Okay, so we're going to start with, we can show the full generation of the carbocation if we want. So we can say that we have this, we have our AlCl3, okay, we can show that. We can then say, okay, this would give us something like that. Okay? So we can show the generation of the carbocation. As I've said before, if you don't show that, that's not the end of the world, as long as you show that you've generated a carbocation. You've said you appreciate that if you add these two things together, it gives you a carbocation. Okay, then we can take, now what I said in the previous one is, you know, this would be considered an unstable carbocation. It's a primary one. We had a question down the front about how do we know? And I said, if you go back to the lecture notes that Professor Osborne did with you, she showed you the difference between primary, secondary and tertiary carbocations. Yes, hopefully. The idea being, the more carbon surrounding the carbocation, they can push electron density into it and they can stabilize. So this would be a primary one. So in theory, it wouldn't be particularly stable, but go back a slide or two and we've said that's fine because we recognize it would probably be, you know, this kind of complex and it would do it as an SN2-like reaction. What I'm worried about is the people talking at the back that I can hear. What I'm worried about is, you know, I don't want you to overcomplicate it. I want you to understand that these things are the same. All you need to do is show you can generate a carbocation. Okay, so we've got our carbocation. We can then do our reaction. We can add to here. Okay. We can then lose the hydrogen. And we end up with that product. So hands up if you ended up with that product. Okay. Did anyone end up with a different product? Because I'm being a little bit mean because actually that's the wrong answer. Okay. It's fine. I am not going to be this tricky to you. I'm just proving the point. And that is, sometimes we have to think about what we generate. So in this case, we've generated this carbocation. But actually, if we were to look at it in a bit more detail, and you will see some of these things happening when you move through the course, is we can do things like, we can move a couple of hydrogens around, there can be a little bit of proton transfer going on. And what can actually happen is this hydrogen can jump across to the carbon that's got the positive charge on. Because what that will do, this is in equilibrium, is it will actually move the carbocation. And what this does is the reason it does it is that this is a secondary carbocation now, it's more stable. So, as I said, I would never be this mean to you in an exam question because that's just trying to trick you. That's not really checking that you understand things. If we were going to do that, we would go through in far more detail the point at which one carbocation would switch into another. All I'm doing now is just explain to you that sometimes these things happen. So when you are looking at, you know, synthetic pathways to make common drugs, for example, you might come across a reaction like this and go, I don't understand why that product isn't what I think it is. And the answer could just come down to that there's this rearrangement of the carbocation to make a more stable one. So if this happens, you would then have your benzene ring. This would attack. You would form that. You would remove the hydrogen and you would end up with that. And this does actually happen. I think it's in the synthetic route to ibuprofen. You can actually have this kind of thing happen. So, you know, it's just to be aware of it, but I promise you I would not be so mean as to ask you that kind of question in an exam. That just would be very unfair and very useless, to be honest. It wouldn't tell me that you knew anything. It might tell me you knew one little thing. I'm more interested in that you can do the general reaction as you move through your degree. Okay.